Hey everybody, in this next video lesson we're going to talk about something called the mole. Now the mole is a concept in chemistry that we use to count really small objects because really small objects are not practical to use. In fact, really small objects like atoms and molecules are so small that chemists don't actually count individual atoms. Instead, we group a handful of atoms together and call them a mole. Now what is a mole? Well, a mole is equal to 6.02 times 10 to the 23rd objects. Now those objects could be really small or really big. It doesn't really matter. It's kind of like a dozen. You can have a dozen eggs and you can have a dozen bricks. All of those equal 12. But a mole represents 6.02 times 10 to the 23rd particles. And so when we're talking about a mole of something, we're usually talking about atoms or molecules. I don't want you to get hung up too much on this number. In fact, I'm never going to ask you to memorize this number, and frankly, we don't use it very often because it's not, once again, practical to count actual atoms. Like, for example, if I say, what is the mass of 12 atoms of something? Well, it doesn't really matter because 12 atoms is so small that you can't even see it. And because of that, we don't really ever use this, but it is a pretty popular number in chemistry circles. It is known as Avogadro's constant, named after some Italian white dude. For your purposes, I'm never going to ask you to memorize this. But we can relate moles to other things that are more useful to us, like mass and other aspects, which is very important moving forward. Now, I found this little video clip that I want to show you, which helps you conceptualize what the mole really is. Take a look.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Now, as you can see, it's a very, very large number used to measure or count very, very small objects. And if you use it to count everyday objects, well, obviously, that would be unreasonable. But it is kind of fun to imagine how many marshmallows there are in a mole of marshmallows. Or if you had a mole of paper stacked, how high would it get? Those kind of things just kind of blow my mind, to be honest. As I mentioned before, a mole is not practical when counting actual objects, and so instead scientists use the mole to count by mass. And in order to be able to relate a mole or this many particles to a specific mass that's useful to us, for example, grams, you need to be able to relate mass and particles. And so let's say, for example, you take 12 grams of the isotope carbon-12, and you use dimensional analysis to convert from grams to kilograms, and then you use kilograms to AMU. Because as you remember, mass of an atom is measured in AMU. One proton and one neutron are both 1 AMU, and it is measured that 1 AMU is 1.66 times 10 to the negative 27 kilograms. So we can convert from AMU to kilogram. So from here, you can go from kilogram to AMU. And one atom of carbon-12 has 6 protons and 6 neutrons, or 12 AMU. So if you use dimensional analysis to cancel grams to kilograms to AMU to atoms, what you get is 12 grams of carbon is equal to 6.02 times 10 to the 23rd atoms, which is equal to a mole. So in other words, what I'm trying to tell you is that 1 mole of any substance is equal to its atomic mass in grams. So no longer when you look at the periodic table and you see the atomic mass or even the average atomic mass on the periodic table as AMU, you should think about how many grams of that substance are in 1 mole. And that weighted average on the periodic table applies in this case too. So one isotope of carbon-12, 12 grams of that isotope of carbon-12 equal this many atoms. You can also apply that to the average atomic mass. So if you take all of the known isotopes of carbon and average them, the average atomic mass is 12.01. In that case, if you consider 1 mole of carbon is equal to 12.01 grams. So simply just take the average atomic mass off the periodic table, and that equals 1 mole of that substance. When we relate atomic mass to grams, we call that the molar mass. Molar as in the mole, so the mass of 1 mole of substance. The molar mass is defined as the grams divided by the moles. The unit is called grams per mole, and if you look, the abbreviation for mole is just missing the E, but that is the abbreviation for mole. Whether you think that's useful or not, it does save you time by just dropping 1 letter off of that abbreviation. So when you're dealing with a compound, all you need to do is, if you know the formula of that compound, is to add up the average atomic masses to get the total molar mass of that compound. So for example, sodium carbonate. Sodium carbonate is Na2CO3. So what we do is we take out our periodic table and we add up all of the masses of each one of the atoms to figure out the molar mass of this molecule, sodium carbonate. So sodium is 22.99, and since there's 2 of them, we do that twice. Now carbon is 12.01, and then we add 3 oxygens because carbonate has 3 oxygens in it, so it's 16.00 times 3. And if you add all those up, you get 105.99 grams per mole, and that is what is known as the molar mass of sodium carbonate. Now, if I'm being honest, this is the first time you've ever seen a molar mass being added up, but you're going to do this so often over the next couple weeks, and even more if you factor in the rest of the year, you'll just come second nature to you. Adding up a molar mass from the periodic table will just be something that you just naturally know how to do. So if you want to try a couple more of examples, we've got lead 2 nitrate and bromine, and if you want to pause the video quick, go ahead and work those out, and then hit play, and I'll tell you what the correct answers are. Lead nitrate is PbNO3 parentheses 2. And chances are, if you screwed up this molar mass, it's because you didn't double the nitrate. When you double the nitrate, you have 2 nitrogens and 6 oxygens. So if you add all those up, you get 331.22 grams per mole. Now, bromine is one of your diatomic molecules. Chances are, if you got this wrong, it's because you just grabbed bromine off the periodic table, but you need to double bromine, and it's 159.81. Now, a word of note, these are not significant values because they're not measured values, and so rounding rules don't necessarily apply, and because of that, molar masses are always rounded just 2 past the decimal. So you'll see almost always I round my molar masses 2 past the decimal. Even if the periodic table has 3 digits past the decimal, I always just round off to 2 past the decimal. Well, that takes care of this video lesson. Thanks for watching.